In the last session we have discussed about fiber lasers. So we have seen the construction of the fiber lasers and different cavity designs. So in the today's class we are going to discuss about dye lasers. So dye lasers is a variety of liquid lasers. So you use different dyes as an active medium. So those type of lasers we call liquid lasers, or in principle, because dye is your active medium, we call those lasers as dye lasers. So in principle we generally use organic dyes solved in the organic solvents. So you prefer the active medium with the wavelength of absorption, you see, then you select what is the wavelength of emission. Accordingly you choose the dyes for your applications. So what happens when you pump with the laser or in a flash lamps to the dye, so the dye will emit the fluorescence. Now if you see, this is a rhodamine G dye. So now you see we are actually shining with a green laser. Okay, now you are seeing a dye is in the liquid solvent. Okay, so you have a solvent, organic solvent. So then you take a dye compound and you disperse in the dye compound, that's it's a soluble in the solvents. So now you have a dye solution. So now once you have a dye solution, you come up with the external light. For example, in this case you have a green laser. Okay, so you have a green laser coming and interacting with your dye molecules. Okay, liquid dye molecules. Now you see whole liquid convert into yellow color. Okay, that means the fluorescence in the yellow region. So that's what in principle what happens. You have absorption around these wavelengths and you have emission in the yellow light. So there is a shift in the emission. So in general we have different type of dyes available. So for example, the most used dyes are rhodamine and tetrasin and coumarin and stilbene, and there are wide variety of dyes are available, and these are all, each dye is soluble in different solvents. So you have to choose the solvent accordingly where these dyes are soluble. Well, that means, for example, rhodamine is easily soluble in methanol. Okay, so then you choose accordingly the dye with the solvent where it's soluble. So ethanol, water, ethylene glycol. So there are different solvents are available. You have polar solvents and non-polar solvents. So you choose accordingly. So that means the dye, where the dye is easily soluble, those kind of solvent you have to choose. So now what is these dyes are actually organic molecules. So generally the chemist will synthesize different molecules. Out of these molecules which gives high fluorescence, those molecules generally you call dyes. Okay, so where these dyes having a extraordinary fluorescence, so they give a high fluorescence. And for example, in this case you see these are a rhodamine 6G dye which has an emission from 570 to 610 nanometers. So now you see you have a broad emission in the yellow region. Now for example, this is your rhodamine G dye, so it has a broad spectral range of your emission from 570 to 610 nanometers. Now there is a acridine red dye, so that can be emitting 600 to 630 nanometers. Okay, so these are different dye molecules as you can see here. So how they are bonding each other with their atomic elements. So now in principle these dye molecules have wide variety of energy levels are available. For example, not only they have a singlet states, also they have triplet states. So when there is a singlet and triplet state, there is always possibility of electron transferring from one system to another system. That means singlet system to triplet system. So when there is a transfer, then you have a loss of energies because your population loss will be there. To prevent those kind of population losses, you generally add certain chemicals to prevent those kind of inter-system crossings. So in that case, you will not worry about the loss of the populations, and also sometimes they have a degradation of the dyes. That means the degradation, the photo degradation, when you apply photons, so the dye molecules degrade. So that means they will have a certain damage to that molecules. Okay, these kind of things can be prevented by having additional chemicals which are appropriate. Okay, so that chemist will know how to do it. So these are all about the dye molecules. So these are mainly organic dyes. So now the assembly and operation of this dye active medium. So you take your dye active medium, and now you have this is a kind of a laser assembly. So what happens, these are the pipelines to have a circulation of the dye. So your dye container, big container of dye, which will be hold at the bottom of your optical table or somewhere wherever it's a suitable place. So you have a large volume of your dye solution. Now what you do, you continuously pump those dye solution to the cavity. So that you have a cavity. So this is one of the mirror and this is one of the mirror. So now this is your cavity. In the cavity you have a dye container. So that means you have a optically transparent a glass container. Okay, so a glass or a quartz, depending upon the wavelength of where wavelength is less absorption for that material, and which is highly transparent. So you have to choose a glass cuvette or a quartz cuvette. So that is a kind of a container. So this container is having a dye solution. So that means you have an external connection to the container so that the dye flows in and dyes flow out. So you have a flow in and flow out should be there. So in that case, now your dye solution is always continuously pumped. So otherwise what happens, if you take a small volume of the solution, immediately you saturate your excited state absorptions, because your atoms, what are they here, because they have in principle their lifetimes are much faster, or when you have a metastable state, so you cannot have a high pumping of your like you have a population inversion created. Once you have population inversion created, then it takes certain time to relax down. So during that time you always have a continuous pumping. So these dye molecules not enough to having a more excitations. That is one thing. The second thing, as I mentioned, there is a photo degradation of these dye molecules. So this photo degradation happens, then these molecules or these atoms will not be suitable for the lasing actions. So to avoid that, what happens, we always change the dye molecules. That means you continue, see, once your excitation over, then your dye molecule will be pumped. So that means you always continuously change your dye system. Your dye molecules will continuously change so that you accept the other new dye molecules always. So that way what happens, you always have a fresh material inside the container. So you have to optimize the flow rate of your dye molecules. So you have to tune to get a good efficient laser power. So these are all the practical parameters to take care for the alignments and the flow rate to see having a good lasing conditions. Okay, so this is your cavity. So in this cavity, so you have a optically a transparent passes. So you have a container here, dye container. So you have a lasing in this cavity. So then you have output come out in this direction. Okay, so this is the assembly and operation of your dye laser. Okay, so now your dye laser is an organic molecule. Their energy levels are looks like this. So this is a typical energy level diagram of the dye molecules. So you have singlet states and you have triplet states. So now you have singlet absorption S0 to S1. So where S0, a lower level, will be a ground state for the system. So now you excite with your pump. So they go to excited state S1, excited states of S1, then can be also possible that you have excited state absorption from S1 to S2. So from S2 to S1 there is a non-radiative decay, so there is very fast decay happens, and this decay not only to this energy levels, this also it's possible to have a decay to this energy states also. Okay, so now you have a non-radiative decay from this S2 to S1 or T2, and from S1 to T1 there is inter-system crossing. So this you call inter-system crossing. It's IC, inter-system crossing. So that means these are all singlet states. So you have a singlet states and you have triplet states. Okay, so now you have a transition from singlet to triplet state. Now if you have electrons are transferred to triplet states, now again if these triplet states are populated, so now what happens, so it can have absorption. Okay, so this absorption also called, it's kind of a excited state absorption, because T1 and T2 are also a excited states. Okay, and also in the molecules what happens, still you have energy levels in higher sides. If the wavelength matches, again you can have a absorption from higher triplet state to even higher states. That's also possible. But what happens, whatever the energy you have transitions, these triplet states in principle mostly non-radiative decays. So now all your population is get wasted, so because this is not a radiative process. So now from T1 to S0 again you have a non-radiative decay, so you don't have a radiation, because in principle we can consider for releasing action. So these are all the population are getting wasted. So that is why we always make sure that there is no inter-system crossing, or you limit the inter-system crossing using adding certain chemicals. So you prevent this inter-system crossing, then you have a very good lasing emission. Okay, so that is about your singlet to triplet state transition. So now what our focus is to having lasing action. Your S1 is populated and you have many states in the S0 state. So there is a transition from your lower level of S1 to some of the states in the S0. So then they have a population inversion. Okay, that is why you have a broad spectrum. For example, in rhodamine G you have around 650 to 700 or 750 nanometers. So these energy levels are available with having a population inversion between your S1 lower state to these states. So then you have a lasing action in those wavelengths. Okay, so this is your radiative transition. So that's where you see the fluorescence. So when you have a radiative transition, and you have chances of having a population inversion, because the spontaneous emission will be trigger the stimulated photons. So this is the typical energy levels of your dye molecules. There is a small changes here and there with the different dye molecules, so your emission will be different. So for example, now if you see rhodamine 6G, so this is a dye molecule. So the solid line is your absorption spectrum and the dashed line is a emission spectrum. So now on x-axis you have a wavelength. So you have an absorption from 200 to 700, around 600 nanometers, and this is your epsilon. So there you can know what is absorption percentage. So these are different peaks mainly because of the triplet states, and these are the peaks because of the singlet states. So now if you see, you have triplet states and singlet states peaks are available in this rhodamine 6G. So now this is your emission for your this peak around 500 nanometer, so that you have a emission. So that means you pump your higher states, you have in the singlet states you have a non-radiative transition, that energy is lost, that is your shift in the fluorescence. Okay, so then you have, this is the emission wavelength. So that is actually emission wavelength is your tunability of your lasing action. Okay, so that is about the rhodamine 6G. So you have different dye molecules are available to get the tunable wavelength range in the visible spectrum. So now you can tune using different dye molecules. The dye molecules are placed in this plot from Siemens 3 to LD700. You can see these are all dye molecules, different dye molecules, and this is the on y-axis you have a wavelength range. So this dye molecule having a give the lasing action or tunability from 400 to 450, and similarly the different dyes can cover up to 800 nanometers or close to 800 nanometers. Okay, so this is the tunability of dye lasers. You whatever the wavelength of laser you want, you can choose certain dyes. So that is a relative energy outputs. So where you will get high energies from above 450 to around 650, you have getting high powers, and the remaining dyes, because you should have a strong absorption cross sections to having a high lasing action or laser powers. Okay, so these are a wide variety of dyes are available in the market. So you can see that the energies can be achieved using these dye lasers, and single go up to it goes to around 250 microjoules of energies. Okay, and this is the first, generally the first femtosecond laser was generated using the dye laser systems. So later on the type software becomes come into the picture, but previously the first femtosecond laser was designed using dye lasers. Okay, so these dye lasers are having giving a tunability. So now if you want to a different wavelengths, you choose your dyes. So you change, you have a different section of dyes, then you pump or you circulate those dyes to having that laser action. So that means if you buy a one system, you have a tunability of 350 to 1000 nanometers. So you have one dye laser system. So now you change your dye in your container, then that gives you a wavelength. So that means it's pretty easy to having a wavelength change. So you change your dye, you get the lasing action. So in solid state lasers, it's not possible for you to change crystals. Okay, so it's not easy to align those kind of things. It's very difficult. But this is like a external container. You replace the dye easily, and you get the whatever the wavelength of interest you want. So you easily get from 350 nanometers to 1000 nanometers. So that is one of the greatest advantage of these dye lasers. So these are the few examples of the dye lasers. As you see, so your cavity is filled with the dye molecules. So now your dyes are flowing out and flowing in using these tubes. So these are dye tubes. So you can have a container at the bottom of your optical table. So these are the pipelines to circulate the dyes. Okay, so this is one of the dye laser system, and you can see the other dye laser system. So these are the dye. So most of the general usage dyes are 6G. Rhodium 6G is very famous and popular for dye laser systems. So this is one of the dye laser systems. So now you have lines of dyes to circulate, and they have additional attachments to convert the wavelengths. So for example, now you see it's a 2 omega, so that means it's a doubling the frequency. So that is called second harmonic generation. So now your laser output will come in this direction, and then the beam is diverted to this direction. So now it will be frequency doubled. So you have a, for example, 800 nanometer is coming out, or 1000 nanometers coming out, then you will get a frequency double. 500 nanometers will be your output. So this is the output port to get a lasing. So these are the few examples of the dye lasers. So then we will move on to gas lasers. So gas lasers, also a wide range of gas molecules are available to having a active medium. So we already have discussed briefly about the helium neon laser. So you have a gas molecules. So that means in general how you measure the pressure. So you have a chamber, you have a gas chamber, you fill the gas chamber with the appropriate active medium. For example, in this case you have helium 90% and remaining neon is 10% will be filled into this gas chamber. Okay, so then what is the pressure of the helium in this gas chamber? The pressure of the helium is 4 torr and neon is 0.8 torr. So accordingly you fill this gas chamber. Now you have a mixture of helium and neon atoms. Okay, so now you have, so in principle you have a electrodes on the other sides. So now you have a cathode to emit the electrons and this is your anode to collect the electrons. So now what do you see? You create a potential in the gas tube. So that means the electron move across the potential. So because for example you have a high potential to low potential, so you have an electron is moving. So when you moving the electron, it acquires the energy. So that is your energy required to receive, go to the excited states. Then you have a different transfers of the states, the transitions to other states. Then where the lasing levels are there, so there you have relaxation to their lower state, giving a photon as an emission. So now what you do, you take this gas chamber and make sure that this gas chamber having a optically transparent those wavelengths. For example, in the helium neon laser, this ends should be transparent to the 632.8 nanometers. Okay, now you place your mirrors. So that is, one is like a highly reflecting mirror and other one is a partially reflecting mirror. So this way you can also construct. The other way is, you can on the glass tube itself you coat with your metals. Like for example, for 632 nanometer, which metal is highly reflectant? For example, you coat the gold or aluminium. Okay, so then you partially coat. So in that case you don't need to place your external mirrors. So you actually, your gas container itself has a cavity. You can make it as a cavity. So you highly reflecting coating on this side and partial reflecting coating on this side. So then your laser cavity itself, your glass tube. Okay, that's up to you how to design your cavity. So now you make this mixture, and when the electrons is going across, so now you will have a lasing action. Once you have a spontaneous emission triggers the stimulant emission. Now what happens in principle, when the energy of the electron is low, that means immediately there is some neon atoms in place. So what happens, there is a transition, but the transition is not radiative. Again it gives as a heat, or it will move heat to the other atoms. So that means you will lose a energy of electron as a heat or a phonons. So that is what happens if you excite the neon atoms. That is why your neon atom should be lower percentage, otherwise your electrons energy will be get wasted when you increase your neon atoms. So now what happens, when the electron is passing through, most probability that the electron will interact with the helium is much higher. The probability is 90%. So that means that when the electron at lower energy of the electron is interacting with the helium atom, now you see you don't have any energy levels up to 19 electron volts. Up to 19 electron volts you don't have any energy level. So that means there will be no interaction with the helium atoms. So that means the electron will, without interacting, it will move on. So when it will move on, it acquires more energy. So when it reaches 19 electron volts or more, then you have a transition to excited states. Okay, so once you have a transition to excited states, now these excited helium atoms also inside the gas chamber, they will interact with the neon atoms with a collision process. Okay, when they collide with the neon atoms, they transfer the energy or the electrons to neon excited states. Once they transfer to neon excited states, they have a transition to the lower states, that is up to 4p and 3p. So then you have a population inversion will be created, then you have a lasing action. So that is the most operational or mechanisms are happening in your helium neon lasers. So now once you have a lasing action takes place between these states, so now you have this 3p state will be radiative decay, that means you have spontaneous emission but there is no population inversion. So in that case what happens, you have a spontaneous emission and then the energy will be wasted as a heat. So that is all about the helium neon laser.